Alright, we're back. Hurrah. Maybe. So what I wanted to do is quickly show you how the 555 timer works so you can get a basic idea. This here is an RS flip-flop with a reset input. RS flip-flop, as you may recall, has a set and a reset, and you're not supposed to assert both at the same time or else it starts to act like an oscillator. This here is a comparator, and when a circuit reaches a certain threshold, then the comparator will trigger. Now when you have an RC circuit, that's a resistor and a capacitor, what happens is it charges the capacitor and then the resistor bleeds off the voltage until it goes to a specific level, and then the comparator triggers, and this goes to reset. When it goes to trigger to a certain point, it goes into the set condition. What you want to do is you want to get it so that the time constant for the RC circuit is well known, and that way you can control when trigger and thresholds are crossed. And so by controlling when the bleed off of the voltage occurs, you can proceed to go to the threshold voltage and cause resets and sets to occur. And that's all. That's all there is to it. It's just a set reset flip-flop with a couple of analog comparators. And you hook an analog circuit to this, and what you're looking for is some kind of guidance as to how to set it up. So this is your typical 555 package. I think it's probably one of the most successful mixed signal devices ever in terms of the marketplace. People really wanted this thing. It's mixed signal because it's got both analog and digital circuits in it. Let's see now. It should give us some kind of guidance. Right, so here's the typical RC setup. Threshold and discharge are both being wired together. There's a trigger on this. They call it a multi-stable multi-vibrator. A monostable multi-vibrator. And there's how you compute your frequency. So you get a couple resistors in here, you get your capacitor in there, you can create a time constant and we'll give you the frequency. The time high and the time low can be adjusted, that's your duty cycle. And so now you can have a mechanism in place for doing direct computations on the 555 and change its behavior. A lot of times what happens is they'll take these charts and they'll just sort of say for a given R1 and a given capacitor, we'll see what the frequency is as a function of R2. So if you just happen to have a 1 microfarad or a 10 microfarad capacitor hanging around, you can plug that in there and figure out how to diddle R1 and R2. If you want the charts for this, a lot of times they'll give you a graph. Although in this particular case, I think the graph is going to be in the data sheet. And I've had a spotty, how you could say, history of being able to open these PDF files. And the other thing that I thought was interesting is this: they got whole books on using the IC timer, the IC timer cookbook. Right? It says all these different wonderful applications for this little timer that you could write a whole book about it. And it was a very popular book in its day. I remember reading through it. And people were doing things like they were building motor controllers and flood detectors and things that would make alarms go off, and synthesizers, organs, all kinds of interesting things. So it's kind of a fun idea. If you can change the resistance of something and it changes the frequency, then you can set up a whole bunch of switches with different resistors and get different frequencies. Now you've got a musical instrument. So things you can do with the 555 timer, it's practically endless, and you wouldn't think so. And it's great fun. Great fun to play with it. Uh, here we are sitting in our basement playing with our timers. Well, it sounds kind of nerdly and all, but it's actually good. Can I zoom in? Can you zoom in? Control plus. Control plus. There you go. So here it is for fixed capacitance. You can sort of see time delay. And they should show you another diagram in here. Free running frequency as a function of capacitance. There we go. So now you can hold the resistors constant and then choose the frequency you're looking for. Not particularly high frequencies, but that's alright. Now if you have a voltage variable resistor, you could use this for a kind of frequency modulator. Now you're starting to talk about building a digital communication circuit, which is kind of cool actually. Or if you wanted to, you could make an FM exciter out of it. And you've got a little FM transmitter. Also cool. Of course, the carrier is relatively low frequency. When we do broadcast FM, we think in terms of megahertz, or actually hundreds of megahertz, right? Because it's usually 91.5 megahertz. That's like a frequency, that's a carrier. But then you look at a deviation of the frequency, it's usually many tens of kilohertz. At least for broadcast. So you get the full data sheet, you kind of have to read through it and figure out what it is, what application you're looking for. But you can see there's a ton of different configurations on this. And here we are talking again about the 50% duty cycle oscillator. So I happen to think that 555 timers are great fun. Let's see if we can get this thing running again.
The via there, being careful not to let that via overlap with other wires, or we can bring it over to this via, so we'll do that. Click on the pad again, bring it up, and bring it over to this via. And now we're connected. That's all there is to it. So we have our board totally wired now. We use the combination of the auto router and some manual routing. Personally, whenever I do board designs, I manually route everything, even very, very complex boards. That's because auto routers aren't exactly perfect. Eagles is pretty good, and for simple board designs like this, it's great. But when you're dealing with high-speed signals or differential pairs, things like that, doing manual routing is generally what I prefer to make sure I get exactly what I'm looking for. But this is looking excellent right now. The last thing we'll do is move some of our silk screens around to get them like we like. Okay, these are looking pretty good. I'm pretty happy with this. Let's say I want to get batteries centered, for example. I showed you how to do this earlier, but here's a quick refresher. I'll change it to go around the top center. Okay. And it's actually showing up on the bottom because if you'll recall earlier, we flipped the battery around. And now I can't get it perfectly centered to where the battery is. I can do that by manually putting it onto a grid that I want. So, like that, for example. Perfect. That's looking great. Okay. Our board is routed, and it's pretty much ready to go. If you want to add some more finishing touches here, you can add your own text. So click Draw Text, enter your name, so we can say Jeremy's board. Now, be careful, because right now this is defined on the top copper layer, which we obviously don't want. We want one of the layers that we'll define to be related to the silk screen. So I'll choose top place, which is what I usually choose. Top names also works. It's just a matter of what layer it puts it on. Later on, when you generate the files for the actual board manufacturer, you'll choose what layers are assigned to which parts of the board, like the silk screen, for example. I'll put that down there, and then I'll rotate it, and move it to where I want on the board. It's also generally good practice to put a revision number on your board, especially because with most board designs, you'll be making several versions of it as you work out bugs. So I'm going to call this Rev A. And I'm going to put Rev A down right here. Nice and easy to see. You can hit Escape, and you'll leave the Enter Text wizard. Okay. I'm feeling pretty good about this board right now. There's one more thing I want to add. Let's go ahead and add a hole so that we can mount it to something. So click the hole button.
Okay, so here's the problem with fabricating this board downstairs in our PC board milling machine. No solder mask, no silk screen. None of the finer touches that we're seeing here can actually work properly when all you have is a milling bit. Only thing you can do with a milling bit is mill out copper and drill holes, and that's it. You could probably cut the boards. You can cut them down, but other than that, you're pretty limited. Plate throughs, not so easy. You have to do that by hand. Probably have to use a drill press and an auger and rivets.
And you can choose the drill size here. What you choose is up to you, keeping in mind I'm working in inches right now. You can change it to millimeters by clicking on the grid. Let's go for about 43 mils. Should be good. And I'm just going to put one hole down in the bottom corner so I can kind of nail it to the wall or do whatever I want with this. Maybe put it on a keychain. You can always edit the size of a drill hole by clicking info, clicking on the hole, and adjusting the drill size. So if you decide you want it bigger, you have to go ahead and make it bigger. Okay, now our drill is bigger. If we hit rat's nest, we'll see that it moves the mask out around from it so that we're not accidentally shorting anything out if we put a metal screw through it or something like that. That would be most unfortunate. Okay, board is done. Before we actually wrap it up though, let's do ahead and do a design rule check. This is basically Eagle's way of checking through the board and making sure it's actually going to be manufacturable. This is a really important step in any design process.
Okay, so design rule check. Design rule checks that Eagle can put into place can be downloaded from your board manufacturer. So if you're going to go to Batch PCB, when you do an upload, they'll do a design rule check too. But you would like their design rules to be right in your system so that when you upload, you're not violating any of their design rules. A lot of times design rules are things like having two traces too close to one another, or having two pads where the components will be soldered too close to one another. You can create your own design rules and check against those, but it's kind of important before you go manufacturing a board to make sure that you're not doing it wrong. And so the design rule check is there kind of like to give you a syntax error or warning when you go and compile your program. It just won't work properly when you go to construct.
Right now we'll use the default DRC checking rules, which should be fine. We'll see how they actually come out and how we do. So hit check. Okay, so we come up with a whole bunch of errors. So let's see what these errors are. One of them is drill size. So we defined our drills to be, for our vias, to be about 20 mils, I believe. My suspicion is that in the design rule check, we set the sizes for our holes to say that they have to be larger than that, basically. So yes, we've set our minimum drill to 24, but we know our board house can support 20 millimeters. So we'll say, don't worry, it's okay for the holes to be 20 millimeters. So let's change that. Yeah, and we can see that those drill errors went away. The only error we have now is a stop mask, and this is a pretty common error. So what's happening here is it's upset about some overlapping layers, in particular the silk screen that overlaps with exposed copper. It's going to get upset about this because obviously you don't want the silk screen printed on top of the copper that you're going to be soldering to. However, once again, most board houses, printing facilities, whatever, will automatically handle removing the silk screen when it's over the copper. So we can actually ignore stop mask errors. I've literally never had an issue with ignoring these in any production house I've used. And that's what all these are referring to. So we can hit fine, clear all, those are gone, and we're happy, and we're good to go. So you finished your board design. Congratulations. There's a few more things that you can do, lots of other options. I won't go into all of them now, but I do want to make you aware that there are user language programs that can do things to adjust your board design and do all kinds of neat stuff. For example, if we go to command renumber, you can renumber things in the order of the board, so it's with a very large board with lots of components, it's easier to find the parts that you want because they kind of go in order. So we'll hit renumber, it changes the layers, and you can see they renumbered it, so like it's R1, R2, R3, and R4, kind of going down from the top left. It's disabled a bunch of our layers, so we can hit all again and show all the layers. So that's basically it. You just designed a board in Eagle. Congratulations. The next step will be to actually get this manufactured. That could mean generating Gerber files. It could mean using the PCB quote tool in Eagle to get it sent out. Or it could mean printing it out on a laser printer and doing it yourself. Again, that'll be more difficult with two-layer boards like this design, but still 100% possible to do that. Okay, so that's it for this episode of my Eagle tutorial series. I really hope you guys enjoyed it and that board design makes a little bit more sense now. In the future, I may go into more details on specific aspects of board design, how you have to be careful about things getting too close to each other, and differential signals, high-speed signals, decoupling capacitors and their importance, power planes, things like that. But for now, this is a simple, high-level overview. Next time, what we'll do is we'll talk about actually how you export this design, how you get it manufactured, and maybe if you're lucky, even how you can get a 3D render of your board design using some very cool user language programs. Okay, thanks everyone for watching. I hope you enjoyed it. All of the source and all the design files will of course be on my website and on GitHub, and please let me know if you have any questions. Thanks for watching.
So let's see what happens if we go to Jeremy's website. Well, you can't get there from here. Oh, there it is. Here's a schematic layout for the 555 timer. 9-volt batteries are convenient to use for these things, although it'll run on 5 volts as well. 555 timers are fairly robust. I don't know if you noticed, but if you've ever tried using the Arduino, they usually put a regulator in there. And if you put 9 volts into a 5 volt regulator, you're fine. But if you go much over 12 volts, you blow it out. So that means if you plug it into your car battery, you blew out your board. If you plug it into your wheelchair battery, that's 12 volts, blew out the board. I'm here to tell you my students found this out the hard way. I told them not to do it. They didn't want to listen to me. So here's this little website. You should be able to download the schematic for the 555 timer from this website. I guess he said it was here. Or not. Jeremy Bloom 555 download. I thought he said it was here on his website. This one? This one? So somewhere in here, you pause with CADSoft, download the CADSoft Eagle here. We got that. You can also download the Eagle library that I used, which is here. This one, tutorial files. And it comes in as a zip. So I guess the thing to do here is to copy, go to the grad assignment, download the software and the tutorial from, and then we can put in the little link and hit paste, hit OK. Then do the layout exercise for a 555 timer. Let's see what we got here. You may need to install the library. Copy, put that in here. Don't forget the library. Don't forget the library. Put that in there. What else do you need? I guess we should look at this. Folder and extract to, let's see, let's give it a name. Blinky Light. Blinky Light. Blinky Light. Good deal. So here's the Blinky Light. Properties. He says it's Windows Shell. You should be able to change what it opens with, right? You got to tell it it's Eagle. Okay, apply, okay. So now if I double click, what happens? Oh, it opens. There you go. It's a good deal. And a go more. So now you've got your little 555 timer. It's all set up and laid out for you. I think I saw the schematic in there as well. Oh, I'm sorry, the board layout. What's this? That's a photo. That's not good. Read me. Yep, it looks like you're going to have to go through the process. This is the little bill of materials. You have to show how many components you're using, the value of the component, the type of package the component is used, manufacturer, maybe even where you're getting it, and somebody even puts in the price. If you put that into a spreadsheet, you should be able to do the computation so that you can show how much stuff costs. I have a bill of materials for my little project, and that includes things like the connectors and all the little ditties, the switch, the jack, a couple resistors, an inductor, and I don't remember what else. I think that's it. It's like $4 worth of parts when you're done. Not a lot, until you buy over 100 of them. Then it adds up quick. But it's not so much how much it costs, it's how much you can charge. That's key. I got to add a few zeros to my Kickstarter project next time, because $3,000 project, it doesn't move the needle for me. But what's interesting is not so much how much money. It's not the funding, it's the crowd in crowdfunding. So I'm thinking you guys are all set now. You've got the little tutorial, you got the schematic. I'm thinking you can do the layout. Yeah, I want to see if you can follow the Jeremy tutorial. You may want to go back to tutorial 1 to learn how to do schematics, but the schematics are actually done. I'd really like you guys to do the board layout. So, you got the little lecture on board layout. Did this thing just log me out?
It expired.
So what happened to all the stuff I typed? Is that gone?
Oh, I don't
Why do people actually like Axiom Mentor? I thought I would try it for the first time. I didn't know I was going to have a negative Axiom Mentor experience. Where was I? In assignments? So it just, is it left here? How do I change the actual work? It's all gone. What was the point of doing that? And so it logs me out in the middle of the lecture while I'm typing up the homework and assembling all the links, and then it says goodbye without saving? This is nice. I like this. What a great program. I mean, even Notepad is less rude than this. Alright. Now I'm really bummed. Well, download Eagle.
So what happened to the PowerPoint?
Huh?
What happened to the PowerPoint? Was there anything removed from there? 'Cause I don't know.
That was Critical Dimensions.
Yeah, but anything else doesn't.
Right now? Not for this. Not for this homework.
For the class, no.
Oh, I was going to do something with de Broglie's wavelength and electron microscopes, but that's been lost. Let's get back to this one thing, okay? Download Eagle, because I hear what you're saying about that. It's a bummer. Install it, and do the layout for a 555 timer using a double-sided printed circuit board. Okay? Follow the tutorial given in copy, paste, and I'm going to write a nastygram to the so-and-sos who are responsible for Axiom Mentor, because I just don't like this. Yes, I didn't want to mention a name. Yeah, I just don't think that's right. I mean, I was in the middle of something.
Someone else logged in on Teams.
I got kicked out because... yeah, I don't either. Yeah, students can upload. What else? Anything else? Save. Display switch hidden. Why is it hidden? I click to make it visible. Alright, so you guys should be able to see this now. I have to say this class ends at about 1:30, so we're right at the end of it. You've got a little layout exercise. You've seen the tutorial. If you need to, you can watch it again at home. I'm going to see if I can upload these videos, see how much of this has been saved and how much is lost. We're having issues. I don't understand why it should time out like that. That should be like a setting. You guys don't happen to know Axiom well enough to know if you can change the timeout, do you? I think you can't, unless you ask. Alright, well, have a good PC board layout experience. I'm expecting you guys to be able to do the layout and then do the upload so that we can open it during class next time. And when you upload it using Mentor. Please don't send me email attachments with Eagle. I'd rather have you guys keep track of your own course portfolios. This is one of those things where it's really good if you can be able to store these things in the cloud, as it were. Dropbox. Well, actually, everybody should have their own mechanism for gaining access to this stuff, right? Materials for the class. Mentor, I think everybody gets course docs, right? And you. Yeah. Does everybody get their own folder?
It's kind of whatever you post after class time.
Okay, but
You
what
can
about
download them.
what about student work?
Work just in, well, for us it says coursework, and whatever we upload, you can download. So yeah.
So do you want to create a separate?
No, we usually, I don't know, I've never done that. Usually just in the homework,
Just in the homework?
like, we download it, yeah, we upload it, you know.
Well, how will you keep your stuff separate from the other person's stuff?
I believe individual. I don't know how we have it set.
Yeah, I mean, where are
Coursework for us.
coursework? Where's that?
Well, for us, it says not for us. For us, it's different. Like we have like assignments like that, and then we upload to there.
Yeah, it's not clear to me how this thing is going to be separate from your thing.
Well, maybe you can decide with me. Yeah, I don't know. If you don't use student groups, then that's how it works.
Student groups?
I don't think you don't use them.
Okay.
I don't know how the teacher set it up, but my stuff always separate from their own.
Yeah, I would like your stuff to be separate from everybody else's.
Under assignments, in the you might have to change the assignments, the settings of the assignments that you made.
Okay, so I'm in student work.
In that assignment, edit.
Student files.
I don't have any files yet. So like I'm pretty sure it'll be separate. So like then you click our name.
Oh, okay. So you guys, when you upload, you'll have your own name associated with your own homework. Okay, good enough.
We can only access our own.
Yeah, these students have no files because the homework hasn't been started yet.
Ooh, are they like not coming? Are they not in the class?
No, I think they're distance learning students.
Oh,
Yeah, we've got a big distance learning contingency here. It's all very exciting. So I got to get back to these guys because we're still recording.